Hey everyone, in this video I'm going to be going through the week 13 PARTE packet answers. Sorry about my setup here if it's a little awkward and distracting. I didn't have a printer at home, so just doing my best with an iPad. So we'll get started. So for this one, we're going to be looking at polymers, and I kind of liked this picture with the streamers because all the little flags here kind of represent monomers on a polymer. So as you know from lecture, polymers are just long strings of molecules that are made up of individual monomers strung together. So for the first question, it asks which of the following is true about polyvinyl chloride, or PVC, which is used in pipes and vinyl records. So if we look at the structure of this polymer, it looks like there are the monomers that you can separate this into is if we make like a break right here, and then we can see that we have a chlorine, a carbon, and then there's two hydrogens, and then we come to a chlorine again. So this right here is going to be our monomer. And as we know from lecture, polymers can be put together in two ways that we talked about. We talked about condensation and we talked about addition. So with condensation, you end up with losing a water molecule because you get something with an OH and then something with an H. And when both of those combine, you'll get like a linker molecule between. So for example, if we have like an OH on one side and then an OH on the other side, and for the condensation we get rid of an H2O. So let's say like this guy and this guy, then we would end up being linked by an oxygen. But here, it just looks like we have a carbon chain with nothing in between. So based on that, we know that it's probably not going to be condensation. So our next answer choice is its monomer is an alkene with 3 carbons. So we already kind of determined that this isn't going to be condensation, it's going to be addition. And we would just have this guy as our monomer. And we know that for addition chemistry, we use alkenes and we add the alkenes together, and that double bond breaks to form this polymer chain. So by the way, an alkene, if you weren't sure, is any molecule that has a carbon double bonded to another carbon. And these monomers, we can see only have 2 carbons on them. So that one is not correct because we don't have 3 carbons on the monomers. So the next asks, the molecular weight of the monomer is 62.5 grams per mole. So let's do some math here. If this is the monomer, then we need to have 3 hydrogens plus 2 carbons plus a chlorine. So the masses of those that you can look up on your periodic table is basically 3 times 1 plus 2 times 12 plus 35.5. Sorry, I'm running out of space here. And if you do that math, you end up getting 62.5. So that one is going to be our answer, but we'll go through the last two to make sure that you understand why it's not these answers. So the polymer is used in pipes because it can form hydrogen bonds to water. First of all, I don't really know why that would be a good idea for pipes. Can't really think of anything off the top of my head. Hint, it's wrong. So something else that we know about hydrogen bonding is we can form hydrogen bonds with hydrogens only with the atoms like bonded only to fluorine, oxygen, or nitrogen, and these are just C to H's, so these hydrogens can't participate in hydrogen bonding anyway, so that one's going to be wrong. And then half of its monomers contain chlorine atoms, so that's incorrect because all of the monomers contain chlorine atoms. Okay, so that is the first one. So number 2, which monomer unit was used to create the polymer shown below? So let's split this into what we think the monomers would be. The simplest way we can split this up is if we break here, then we have a carbon with this phenyl group, and then this is called phenyl, by the way. Benzene is another name for it, but that's spelled like this, not phenol, because that's something different. So that's what that group is. And then if we keep going, another carbon, and then we see that we have the same repeating unit here. So this is going to be like our monomer. But this was made with addition chemistry. So what happens with addition chemistry is you have an alkene, so I'll just represent this by a double bond, plus your chain. And then what happens is this double bond breaks, and you just add it to the chain. And I will color this a different color so that you can see it better. So let's say that this guy is green. We will add it to the end here. So hopefully that makes sense. And then, so we can draw what this basically would be then. So it'll look like this with our phenyl ring or benzene. And then we will have a carbon, and then we'll have a double bond here because this is how we add it. So let's see if any of these match with what we just drew. So this one is no, this one is no. This one has an extra carbon on here, but it looks kind of similar. This is what we drew because I didn't draw the hydrogens on here. But if you count up, each carbon has to have 4 bonds. So this carbon has 1, 2, 3, so it has another H. This carbon has, sorry, I'm drawing on top of that, 2 more. So this looks like the exact same thing as answer choice D. And then this one is obviously wrong because we don't have 2 rings on each monomer. All right, so 2 will be D. On to the next problem. So this one asks, the reaction between a dicarboxylic acid and a diamine to form polyamide polymers like nylon is an example of which of the following types of polymerization reaction. So a dicarboxylic acid is anything that has any molecule that has a carboxylic acid on one end. It has some stuff in the middle, we don't know how long it is, and then a carboxylic acid on the other end. And then, so we get that because di means 2, and then carboxylic acid. And the same thing with a diamine is going to be an amine or a nitrogen group on one side, and then the same thing on the other side. So when we do polymerization with this is going to be what do we have to use to join these together is what this question is asking. So we talked about addition chemistry needs an alkene to add to one side. Then the other option that we learned about was condensation chemistry. And with condensation chemistry, you need a hydrogen on one end, and you need an OH or a hydroxyl group on the other end. So if we look at this guy, we do have a carbon, or a hydrogen on this side. We have two actually. And then we have the OH or hydroxyl group on this side. So if we were to draw this linking together, we would end up with, so here's the nitrogen, just one of the H's because we got rid of one of them if we're linking it together. This is the bond that just formed, and I will draw that just as a single bond to not be confusing. And then we lost this OH. So now we have, oh, sorry, I'm drawing on top of this, ran out of room. This kind of thing, where we have the double bonded O. So this bond that we formed is called an amide. So we just said that we formed polyamide polymers, which is what this is. So the mechanism that we went through here was condensation, because the molecule that we lost was an OH from the dicarboxylic acid and an H, which is H2O. And we know that as condensation polymerization. Right, number 4. So many over-the-counter laxatives include polymers of polyethylene glycol, or PEG, PEG. One such polymer of PEG has an average molecular mass of 4,400. Approximately how many repeating units are present? So we need to find the mass of this repeating unit. So let's draw in the hydrogens so that we know how many we need to add to our structure, or to our molecular mass. So this carbon right here, I'm drawing in 2 hydrogens. And that's because this carbon has 1, 2 bonds. And then this guy over here also needs 2 hydrogens because it only has 2 bonds to other things. And hopefully that makes sense why I'm adding those, because all the carbons have to have 4 bonds. So now looking at this repeating unit, we have an oxygen, which is 16. We have a carbon, which is 12, and another carbon, which is 12. So that's going to be 12 plus 12. And then hydrogens are all 1 gram per mole. So we are going to say that we have 4 hydrogens, so plus 4. So 16 plus 12 plus 12 plus 4 is equal to 44 grams per mole. And then we will use the formula of the average molecular mass over molecular mass of monomer. So that's what MMM means, of a single monomer. And then that is going to equal the number of monomers. So if we use 4,400 over 44, we get 100. So the answer is going to be C. All right. Next question. We'll go through this one just really quick. Condensation polymerization between a carboxylic acid and an alcohol will condense out which of the following small molecules. So we're going to be looking at a carboxylic acid, and an alcohol. So an alcohol is just anything with an OH. So it looks like we're going to be getting rid of an OH on one side and an H on the other side. So we'll end up with this structure right here, which is called an ester. And we will also have an H2O molecule because OH plus H is H2O. So the answer there is A. So that should be something you memorize. All the condensation polymerizations that we look at that have an OH with an H are just going to have water. So next, starch is a branched polymer of D-glucose, and cellulose is a linear polymer of D-glucose, both found in plants. Given the concept discussed in the polymer lecture, which is expected to have the longest intermolecular forces between chains? Okay, so this one, you kind of need to visualize a little bit to understand, but once you can visualize it, it makes a lot of sense and it's pretty easy. So if starch is branched, that means that the structure of it, will put starch in red. Starch is going to have like lots of branches on it. And then cellulose, we will do blue, is just going to be linear. So if we have the same amount of mass with this guy and this guy, which one do we have more surface area? Obviously this one, right? Because your only surface area that you're able to use is just on the outside, whereas this, we can, with the cellulose, we can use every possible area around, all the way around, instead of it just being like a ball. That's a connection with biology also. As the volume increases with something that's round, it has a relatively small surface area to anything that's more like flat. This is kind of why on the walls of your intestines, your cells have what are called villi and microvilli, which are just kind of like hairs to increase the surface area. So at the end of the day, we're looking at linear molecules having more surface area. So those are going to have a stronger intermolecular force. And then also, if you are larger, are you going to have a stronger intermolecular force or weaker? It's obviously going to be a stronger force between a larger molecule. So if you're thinking about like strips of Velcro, you can use like a super small strip of Velcro to hold like something small up on like the wall or something like that. But then like skydivers will use like strips of Velcro to like literally, I think, put like their parachutes on themselves, or like strap each other together, and those are withstanding huge shear forces, more than just the typical gravity of like holding a small thing against the wall. So larger area is going to have more interactions, so the answer here is going to be D, because we have bigger molecules and they're linear. So which of the following biological molecules is not a polymer? So DNA is a polymer of what are called nucleotides. So if you like see the structure of DNA, it looks just like it's a double helix shape, and it has all of these little, what they look like rungs, but they're just, you have like the outside chain. So this is like this part of the molecule is like the rung part, or excuse me, about it's the outside of the ladder, and then you have on the inside the rungs. So the repeating unit here would be actually just like half of this because these pair together. So with this picture, we have 4 monomers. So DNA is definitely a polymer. Muscle protein, proteins are just basically just strings of amino acids. So that one is a polymer. Hair is made of protein, and it kind of curls around or just stretches straight depending on the type of hair you have with a bunch of different proteins, so it's almost like a polymer of a polymer. So that one is. Cell membranes are not held together by any covalent bonds. They're just interactions between these molecules called phospholipids. And these molecules are in a 3D form. So they do not form polymers. Cellulose we just talked about. Cellulose is going to be that linear chain of glucose molecules. So the correct answer here was cell membranes are not polymers because they form a 3D structure like a sheet, which covers entire cells. So that is the answer there. Number 8, IR spectroscopy is an analytical technique that helps scientists determine what characteristic of molecules. So when we look at IR, we are looking at what frequency is absorbed by the bonds between the atoms in your molecules. And that helps you decide what type of bonds you have. So this one is kind of just a knowledge question, and the answer would be that it helps determine the functional groups and the molecular structure, because you can see like the difference between a C to O bond versus if you have like a C to double bond to O. So we can't determine the molecular mass from things, but we can see the different functional groups that you have based on different characteristic like C to O or C to N or C to double bonded to C. So we can't necessarily see the boiling point or the molecular mass or the molar mass or the density. We have other ways of measuring those things. So what functional group is used to form addition polymers? This is back to what we were doing earlier. Addition polymers are made with a chain, and then you add an alkene to it, and that double bond breaks, and we'll use red to represent this guy. So you break your double bond and add those 2 carbons to the end. So our answer here is going to be B, alkenes. So the frequency of molecular vibrations is directly dependent on which of the following. So this is a little bit of a physics question. Let's go through each of these and determine if they will change the frequency of molecular vibrations. So the type of molecular motion is definitely true, because the way that molecules can move, they can either kind of move like closer and further apart like this. They can just move back and forth. They can have symmetric versus asymmetric stretching, and those will all change the frequency of your vibrations. So that one is true. The bond strength will also make a difference. So for a practical example of this, if you play guitar, or if you've like seen a guitar played and you know a little bit about it, you know that some of the strings are thicker and some are lighter than others, and that changes the frequency of the sound that's produced from them, because the thicker strings will make a lower sound, and typically the lighter strings will make a higher sound. And so we can talk about bond strength being like a thicker or thinner string, so that will definitely make a difference. Atomic masses also makes a difference. So if you think about, you can really compare bonds to springs a little bit. And if you think about like attaching two things to the end of like a slinky, so if you have, like let's say you put like two balls on the end, and they're about the same size, and you like move it back and forth so that they kind of come in and stretch apart like that and oscillate. We call that oscillation. It's going to be a different type of motion or a different frequency than, let's say, you put like a pretty small, like a bouncy ball on one side and have like a bowling ball over here. So the atomic masses definitely make a difference here. Also, even if these are like, let's say this one is like 5 grams and this is 5 grams, and if you increase that to like they're both like 50 grams, then it's going to make a difference in the frequency that you see. So the answer here is going to be E, all of the above. E, or A, B, and C. So now we have a math question. What's the energy of photons contributing to the indicated peak in the IR spectrum of methamphetamine? So we can use an equation for this one that we know from before, and that is going to be energy is equal to the constant H times C times the wave number, V. And we need to convert our wave number, which we're given, 3254 inverse centimeters. We need to convert that to inverse meters because we need to know joules, and joules is in a unit that is aligned with meters, not centimeters. So what we'll need to do is to find the energy, we can have H, which is 6.626 times 10 to the negative 34th times C, which is the speed of light, 3 times 10 to the 8th times our V, which is 3254, but it's in inverse centimeters, so over centimeters. So to get it to meters, we need to put a conversion factor here. So to cancel it out, this can get confusing because remember that your centimeters is going to be on the bottom. So we want to put the centimeters on the top over here to get rid of it because we want 1 over meters. So we'll multiply it by 100 centimeters to get rid of that inverse centimeters and get 1 over meters. So if you do 6.626 times 10 to the negative 34th times 3 times 10 to the 8th times 3254 times 100, you're going to get 6.47 times 10 to the negative 20th joules per photon. And that's going to be answer choice A. All right. So I just copied the spectrum to this question here because we're asking the indicated peak in the spectrum is most likely due to which of these types of vibrations, given that here's the structure of methamphetamine. So on the next slide, I have a chart comparing the type of bond and the wave number and intensity that you can see on your IR spectrum. So let's look at each answer choice and see if our frequency, which is 3254, is going to be about correct. So hopefully I don't give you motion sickness by looking at this, but by switching slides all the time. But the first one says C to C double bond in the ring. So we'll look down here and we have a C to C double bond, and that's going to be 2260 to 2100. We know that that one is wrong because this is 3254. C to C, we don't really see those in your IR because they just won't be a very strong signal, and that's not even included in this chart. An N to C bond on the left of the molecule, or an N to C bond on the right. Let's look and see if that's a possibility. So a single bond C to N is going to be 1230 to 1020 with a medium intensity. So it is a medium intensity, but it's not in that range. It would be much lower over here. So that one is not going to be correct. And then finally, an N to H bond is going to be 3500 to 3300, and it's medium and broad. And that's correct. We do have a medium peak that's broad, and it's 3254, which if you round up, that's like 3300. So this one is going to be correct. So E is the correct answer there. And then finally, number 13, I shouldn't say finally, this isn't the last question, but which type of light is able to break chemical bonds? So this is something that was mentioned in lecture. Microwave can't break chemical bonds. That's just what we use to heat things up. If we think about the microwave that you use in your house to heat up food, that just vibrates water molecules, which increases the heat in things. It can't actually break chemical bonds. Visible light can't break chemical bonds because then you could literally get cancer from being inside and turning on a light. By the way, cancer is typically caused by damage to your DNA, where you have some source that's breaking the chemical bonds, which causes your cells to not be able to fix them very well, and then you end up with mutations because you broke the bond and your cell had to fix it, and it messed up the code a little bit. So kind of like if you had like a book and you like dropped the book face down in the mud and had to rip out a page. Mutations that cause cancer are kind of like that. So UV, ultraviolet light, if you think about if you've ever seen an ad for sunscreen, it always says that it blocks UV light from the sun because that's what's dangerous, and that is the correct answer here because UV light is the type of light that can break chemical bonds and cause skin cancer, among other types of cancer. And then infrared, IR does not actually break the chemical bonds because then we would not be able to see the absorption peaks by putting IR. It's actually just absorbed and it makes the molecules move. And then radio wave, that also does not break chemical bonds, or it would be probably dangerous to go outside if we were having, or it would be dangerous to stand next to your radio or something like that, which obviously it's not. And which of the following bonds would have the highest stretching frequency? So high frequency is proportional to high bond strength. So the stronger your bond is, the higher your frequency is going to be. And what we know from the last exam is that the stronger your, or the more bonds that you have, the stronger they are. So C to C is going to be the weakest, and then a double bond is going to be stronger than that, and a triple bond is going to be even stronger than that. And then we also have oxygen triple bonded to oxygen, or oxygen double bonded to oxygen. So we've determined that the answer is not going to be this one, or this one, or this one. So we need to decide between C and D. So when we look at the bond strength, so these would be similar, but oxygen is also able to hydrogen bond with other things like water because it has these lone pairs on it, and that can reduce the strength of this bond because these bonds are being pulled on, or like the electron density that contributes to these bonds are being pulled away by interactions with other molecules like hydrogen. So in this case here, C is going to be correct because we're not going to have those interactions that will draw away from the C to C triple bond. All right, and next question. In order for molecular vibration to absorb IR light, the vibration must cause which of the following changes in the molecule? A change in the melting point. We didn't talk about melting point really much with IR because they don't really have anything to do with each other, so that's a hint that that one is wrong. A change in the molecular dipole. So let's say we're looking at the stretching frequency on water. So sorry, those are just supposed to be single bonds. When we look at IR having a stretching frequency on the water molecule, something that we can look at is this bend here. I guess that wouldn't be the stretching frequency, it would be the bending frequency. So this water can bend so that it's wider, or it can bend so that this angle is really tight and small. So that would change the dipole moment because if this is our partial positive down here and this is our partial negative, so if you do some vector addition, if your dipole moment is like, I'll draw with another color so you can see, is this way and this way at this angle, then we get a net of like that long. With this, your angle is much different. It's much wider. So you have a much shorter net because most of our dipole is kind of used against each other, and it cancels out, so it has a smaller dipole moment. And then here, they're both in the same direction almost. So our net is going to be longer. So this changes the dipole moment, and that is what is measured with IR absorption. So this one is going to be the correct answer, but we'll also go through the rest of these answers to show why they're wrong. So obviously it's not going to be none of the above because it's the change in the molecular dipole. A change in the molar mass is not going to happen because we're not removing molecules and we're not adding, or excuse me, we're not removing atoms and we're not adding atoms. We're not breaking any chemical bonds. And a change in the electronegativity. So we're not like shooting this with electrons, or we're not changing the properties of any of these atoms. We're not doing any nuclear chemistry. So that one is also going to be wrong. And finally, our last question. So we're looking at a wave number of 1710. And we're going to look at which functional group that represents. So I have on the next page the same table as before. So let's just go through all these and see which one it most likely is. So an alcohol is going to be an OH bond, which is right here. OH alcohol is going to be 3650 to 3200, strong and broad. That is not what this is at all. This is not very broad, but it is strong. Alkyne is going to be a C triple bonded to a C. So sorry about the resolution here, but that's what this one is, and it's 2260 to 2100. That's also out of our range. An amine is going to be a C to an N or an N to an H, because an amine has this structure here. Also, these H's could be C's. They could be other carbons, depending on the type of amine that you have. And by the way, we'll mark these out. So let's see if it could be an amine. So we'll look for C to N or C to H. C to N is going to be 1230 to 1020, also out of our range. And N to H is going to be 3500 to 3300, out of our range. So we'll look at carboxylic acid next. The OH from the carboxylic acid is 3300 to 2500, so it's a large range, and it's strong and very broad. So we could have, with a carboxylic acid, the structure of that group is this. That's the rest of your molecule. Sorry, that's an H. Need to work on my handwriting. So things that we could be looking for is a C double bonded to an O or an O to H. And while we already saw that the OH is not going to be present because that was 3500 to 3200, that's not present. We do notice, just the OH by the way, I'm not sure if I messed that up, but the C double bonded to an O is going to be 1780 to 1650, which is in our range. But we don't observe this OH because that OH is going to be 3650 to 3200 strong and broad, and we don't see that. Instead, we just saw this part of the molecule, but we didn't see this. So a ketone is a type of carbonyl, or a C double bonded to an O, but it has carbons on both sides. So R represents different carbon groups. So this case, it's not going to be an amine, it's not going to be a carboxylic acid, but it is going to be a ketone. Alright, so that wraps up this video, so hopefully all those made sense, and feel free to email your TAs if you have any questions, or not email your TAs, excuse me, type a Piazza post. Alright, have a good day, guys.